In this video, we define the reaction Gibbs energy. Alright, we're going to be looking at chemical reactions and try to see if we can understand stability and spontaneity in chemical reactions. So this will be a case in which we have a reagent A perhaps turning into a product B. And the question that we ask is this reaction spontaneous or not, and what is the change in Gibbs energy? Until now, what we know how to calculate is what will be the reaction Gibbs energy if both species would be at the standard state. But as we have seen in a prior video, this is very limiting because most chemical reactions in our body are not going to be at the standard state. Notice that for solutes in solution, the standard state is 1 molar, and there are very few species, if any, that have a 1 molar concentration in our bodies. Okay, so the idea would be to go beyond the calculation of the reaction Gibbs energy at the standard state and just be able to calculate it for any type of concentrations that we want, including those inside our bodies. Alright, so the question is, well, what is the definition of this Gibbs energy? How can we calculate for a chemical reaction? Well, we know that the process that we're going to study is as follows. First, you have A going to B, and then we're going to assume that a tiny little bit of A, a differential of N of moles, are going to turn from A into B. The question is, how does the Gibbs energy change upon that transformation of A into B? Alright, so before the change in moles from A to B, we can calculate that the initial molar Gibbs energy would be equal to the number of moles of A that we have times the contribution per mole of A to the molar Gibbs energy, and that is exactly what we call the chemical potential, plus the number of moles of B that you had, if you had any, okay, multiplied by the molar Gibbs energy of B, which is the same thing as the chemical potential. Well, now we assume that a little bit of A has disappeared and turned into B. The question is, well, what would be the Gibbs energy after that reaction has taken place? Okay, so after that reaction has taken place, the final Gibbs energy would be equal to the number of moles of A that you had initially minus the little bit that has reacted, multiplied by the chemical potential of A, okay, plus the contribution of B. Now B has a few more moles, okay, that have been generated during the reaction, so that would be the number of moles of B plus this differential of N multiplied by the chemical potential of B. Alright, so the change in Gibbs energy, therefore, is going to be equal to the following. Differential of Gibbs energy is going to be equal to the following. Okay, notice how the number of moles of A, chemical potential of A, number of moles of B, chemical potential of B are going to cancel, and only the terms that depend on the differential of N will survive. Okay, so we have here minus differential of N, chemical potential of A, plus differential of N, chemical potential of B. Okay, can take common factor of the differential of N, and this is going to be equal to the chemical potential of the product species minus the chemical potential of the reagent species. Alright, so here's how the definition of the Gibbs energy is. The definition of the Gibbs energy is a molar quantity, so we just take the change in Gibbs energy and divide over the number of moles, and this is simply going to be equal to the chemical potential of reagents minus the chemical potential, of products minus the chemical potential of reagents. This is what we call the reaction Gibbs energy. Alright, so this is very interesting because it again allows us to calculate the reaction Gibbs energy at any set of concentrations or conditions that we're interested in, but it also reinforces the concept of a chemical potential. Notice what's going to happen here. If the chemical potential of A is greater than the chemical potential of B, if the chemical potential of the reagent is greater than the chemical potential of the product, then the reaction going from reagents to products will be spontaneous, right? That will be negative, which means that the reaction will be spontaneous if we're working at constant pressure and temperature, right? So this again reinforces the idea of the chemical punch. If A has more punch than B, then A will transform into B. Okay? Conversely, if B has a higher chemical potential than A, then the reaction A to B will not be spontaneous. Instead, the reverse reaction, B going to A, will be spontaneous. Okay? So again, notice that we work really hard to be able to calculate what these chemical potentials are and how they change with concentration, and this is where they now appear. They give us a very convenient way to calculate what the reaction Gibbs energy is. Now, something extremely important is that these chemical potentials change with concentration. Right, notice that the generic form for the chemical potential of a substance J is equal to the chemical potential of J reference state plus RT natural log of a measure of concentration, activity of J. Right, so the concentration, suppose that J now is A. As the reaction is making progress, the concentration of A is falling, is decreasing, and that means that you're actually changing the chemical potential. So what that means is that this value is not unique, right? It actually depends on a particular set of concentrations, and as the reaction takes place, then that value of the reaction Gibbs energy will change as well. Okay, because again, the concentration of A is decreasing during the reaction going from left to right, and the concentration of B is increasing as you're actually generating B from A. All right, so something interesting again is that this Gibbs energy actually changes during a reaction. And a way to visualize that is to actually draw these graphs that show how this reaction Gibbs energy might proceed as a function of the reaction progress. Okay, so suppose that this is 0% complete reaction, and this is 100% complete reaction. Okay, and again, what we're trying to see is how this Gibbs energy changes. Right, so a typical graph would be something like this. Okay, so let's see what this is. Notice that if we actually look at the slope of that line, that will be the first derivative of the Gibbs energy with respect to the number of moles, okay, or percent completion if you want to. We're going to call this reaction progress. Right, notice that, again, that slope of the line is going to be equal to differential of G over differential of N, which is exactly the same thing as a reaction Gibbs energy. Clearly, the slope of this line changes as the reaction takes place. At the start of the reaction, when we have that very little of A is turning into B, or there's very little of A turning into B, that means that you essentially have mostly reagents. What happens here is that the slope of this line is negative. And that means that the reaction as written in the A to B direction is spontaneous. When you come to this point, okay, the slope of that line is still negative, meaning that this value is negative, and the reaction going from A to B is still spontaneous. Suppose that we actually now get to a point where we have about 90% completion. Okay, so in your mixture you will have 90% B and 10% A. What we actually see here is that the slope of this line has changed now. Instead of being negative, it's positive. And what that means is that the reaction is actually not spontaneous in the A to B direction. Instead, it will be spontaneous in the B to A direction. Right? So if you get to a situation in which you have 90% B and only 10% A, then B will react to generate B and displace the reaction from right to left. Okay? When you come to this point, which is about 65% or so completion, okay, what you actually have is that the slope is 0. At this point, we have reached chemical equilibrium. Okay? So what will happen is that the tendency of A to generate B is exactly the same as B to generate A, and the reactions will be taking place, but the rate of A to B will be exactly the same as the rate of B to A, and the concentrations will no longer change. Okay, so let's summarize this graph by looking at operationally how the reaction will take place. Initially, you will start the reaction with 100% A and no product. Okay, this will be this point. You let the reaction go, and the reaction will be spontaneous. Okay, so A will be turning into B. Now you'll have 90% of A, 10% of B, 80-20, 70-30, 60-40, then 50-50, and the reaction will continue to go because the slope is still negative. Okay, then when you get to about 65-35, then the reaction, you will see that you cannot make it progress anymore. Okay, you reach the point of chemical equilibrium, and then it's not possible to generate an excess of B beyond 35% with respect to 65% of A. Conversely, if you start a reaction with 100% B and no A, then the reaction will actually proceed in the backward direction, okay, 90% B, 10% A, until you get to about 30% B and 65% A. There you will reach chemical equilibrium, and that's where the reaction stops. Okay, so again, in this video we have defined what the reaction Gibbs energy is. And again, notice that this is simply going to be equal to the chemical potential of products minus the chemical potential of reagents. Now, in the next video, what we're actually going to see is a quantitative way to calculate delta Rg from our knowledge of the chemical potentials that we have derived in prior chapters.